Okay, so in this unit, we're trying to figure out what at the nano level causes substances to have the properties that they do. And one thing we're looking at is specifically what state of matter is it in? Why are some things at the same temperature solids while other things are liquids and other things are gases? So we're going to look at several different types of substances and look at the forces that hold them together. There are several different types of solids: ionic compounds, metallic compounds, molecular covalent compounds, and one we haven't talked about yet called macromolecular compounds. And so each of these is held together by a different type of force, and therefore it's going to have different properties. So in this video, we're going to look at the first two, ionic and metallic, and kind of break those down and look at the nano level, what holds them together, and why do they have the properties that they do. Now, the first one, ionic, we've already talked about quite extensively. So you know that ionic compounds are held together because you have ions. You have things that have opposite charges. And so because they're oppositely charged, they're attracted to each other. That opposites attract saying is called an electrostatic attraction or a Coulombic attraction. And that's a pretty strong attraction. The positive is attracted to the negative, is attracted to the positive, is attracted to the negative. And so it's a very strong force that's holding all of these particles together. Now keep in mind, remember that ionic compounds are not made up of molecules. There are no discrete molecules here in this guy. There are just a big network of positive, negative, that holds it together. Now because it's a very strong force and there's no weak points in this ionic compound, we've mentioned that they have very high melting points. They need to be thousands of degrees Celsius usually before we can melt them. And because of that, we've also mentioned that all ionic compounds are solid at room temperature because of that really strong force holding all the particles together. And because it's that network of positive, negative, they're actually quite brittle. If you push one of those rows and hit it with a hammer, push one of the rows across, then you get a negative next to a negative, and then a positive next to a positive, and negative next to negative. And so it just splits. Instead of denting or anything like that, you hit it, it just shatters. So ionic compounds are kind of behave like glass or peanut brittle in that they are brittle because of the properties. All of the electrons are tied up, and so as a solid, ionic compounds do not conduct electricity. If you had a cube of salt and hooked some wires up to it, it is not going to conduct electricity. However, ionic compounds generally do dissolve in water, and if you have a solution with an ionic compound, and it will conduct. Remember, when ionic compounds dissolve, what happens is they split apart into the two separate ions. So if you have salt water, you have sodium ions floating around in there and chloride ions floating around in there. And so those ions are able to carry a charge from one side of that beaker to the other, and so they're able to conduct electricity in a solution, but not as solids on their own. So we're pretty familiar with ionic compounds. Now let's take a look at something a little bit different. What if I have a metal? What if I have, say, a chunk of aluminum? How is that held together? So if we look at this aluminum can here, of course it's an element. It's made up of aluminum atoms. Now let's just think about aluminum atoms for a minute. Okay, here's our nucleus in the center, and then we have the couple shells of electrons with its valence electrons on the outside. Now think about metals. How strong is the attraction between the nucleus and the valence electrons in a metal? Well, hopefully you remembered and answered that it's not very strong. The ionization energy of metals are fairly low because, again, we have a fairly small number of protons in here for any given energy level. So a key to understanding how this is held together and how metallic bonds form is understanding that there is a weak attraction between all metals' nucleus and their valence electrons. And so what we're going to see here is when we look at our aluminum can, we're going to look at the nucleus and the rest of those inner shell of electrons. We're just going to call that the kernel or the core of the atom. And so in our case here, you can see we have a bunch of our kernels, the nucleus and the inner shell electrons, and then here's the valence electrons. Now, since these valence electrons are weakly held by that kernel, they're actually just as attracted to the aluminum atom next to them as they are to themselves. And so those valence electrons are free to flow very easily from one atom to the next. So we have kind of a random just flowing. This is often referred to as a sea of electrons, just to show that they can flow from one to the other. So what we have here in this case is a lot of atom kernels that are essentially sharing electrons. It's not the same thing as a covalent bond where you have a back and forth going on. It's just this loose sea of delocalized, and that's what holds them together. Okay, so here's again our picture for this. So, what is it that holds the metallic metals together? Well, we call them metallic bonds, and it's basically this sharing of electrons. Again, what causes it? Well, very important fact, we mentioned that they have a weak attraction for those valence electrons. And because of that weak attraction for valence electrons, see, here they are, they're very weakly held in by the kernel. These valence electrons are free. Hey, I'm attracted to this guy. Oh, I'm attracted to this guy too. Okay, I'm just attracted to this guy. So they're just kind of wandering around, flowing like we saw in that little animation. Okay, so that's what we mean by delocalized. They're not bound to any one atom. And this big sharing sea of electrons is what holds it together. Okay, again, here's what we call the positive core. This consists of the nucleus and the inner levels of electrons, and then we're just focusing on the valence electrons here. Okay, so they are loosely shared, not the same thing as covalent. It is a delocalized sharing of electrons. Okay, and it's often referred to, almost every book I've seen or video, they refer to metallic bonding. They use this phrase, sea of electrons. Okay, and again, because they're sharing, that forms the bond holding them together. Okay, now because they're held together that way, we can talk about the properties that we're going to have. Again, there are no molecules here, so there's no individual units that have weak points. So it's a fairly strong force that are holding these together. So as a result, metals have pretty high melting points. I mean, think about the metals, they're almost all solid at room temperature. Okay, so I wouldn't quite put it up as high on average as the ionic bond. Okay, ionic bonding I'd say is on average a stronger force. Okay, there are exceptions, overlapping areas, but most ionic compounds have higher boiling melting points than metallic or just a little bit below them, but it's still fairly high. Now, imagine that sea of electrons that we just looked at. Because those electrons are delocalized and free to flow from one atom to the next, this explains why metals can conduct electricity as a solid. It really matches beautifully, explaining why they have the properties that they do. It also explains why metals are malleable. There's no positive, negative, positive, negative. So if you bang one end with a hammer and one of the kernels moves, it's really no big deal. The electrons, it can absorb it, it can move position a little bit, and it doesn't break. It just bends and changes shape. Okay. Now, of course, metals are very important. We use them a lot in everyday life, but a lot of times we don't use metals as is in their elemental form. A lot of times we have mixtures of things called alloys. And you can see here our definition. An alloy is a homogeneous mixture where at least one of the components in it is a metal. So again, because they're alloys, they're essentially held together by our metallic bonds. So they still have our sea of electrons. And so most alloys conduct electricity pretty well. But in a lot of cases, it changes the properties a little bit. Even though it's still just a mixture, basically you just have things combined together. And so for example, stainless steel. Okay, iron is the main ingredient in steel. One of the bad things about iron is that it rusts. So that's a problem if I'm making things that are going to get wet. I don't want them to rust. So we've invented stainless steel, which adds a layer of some chromium atoms to our iron. Now, chromium reacts with oxygen to form a chromium oxide. And that chromium oxide is pretty stable. And so when the chromium atoms react at the surface of your steel with oxygen, you have that chromium oxide, which is now pretty inert. And so the oxygen from the air can't get to the rest of the iron in there. And so stainless steel doesn't rust nearly as easily as regular steel. So if you're buying a grill to keep outside, it's a good idea to have a stainless steel grill. Okay, now when we talk about alloys and we want to make things, there's two major categories of alloys and which have different properties. And the way we tell what type of an alloy it is by how the size of the types of atoms compare to each other. You can see in our picture here, in some cases, we have two types of atoms that are very similar in size. See here in this first example, these are very similar in size to each other. If we look at our jar of rocks here, we can see that in this example down here, that the rocks are all very similar in size to each other. So these two pictures kind of go together, representing one kind of alloy. And in other cases, we might have a big difference between the size of the particles. Here we have one kind of atom here, and here's a different kind of atom, very, very different in size. So down here in our picture, we can see we have our rocks that are in here that are much bigger, and then the sand particles are way, way, way smaller than that. So that's going to be a different type of alloy, okay? They might be very different size like over here, or they might be similar in size like we have over here. So let's look at that sand example first. When we have a big difference in sizes, it is called an interstitial alloy. Okay, and so our definition is that's the kind of alloy we get when we have a very different radius of the particles that are involved. And this usually happens when we combine some of our smaller elements with metals, like if we use boron or carbon or nitrogen or oxygen to make an alloy with a metal, we'll usually have an interstitial alloy. And if we think about what happens here, it really causes it to have different properties, because what happens here is the small particles actually fill in the gaps. We can see that well on our picture here. And if we think about our picture of the rocks, okay, imagine that I had that first picture back where we had just plain rocks that were in here. Okay, everything's about the same size. So if I come along and I were to punch this, probably not the smartest thing to do. I don't usually punch rocks, but if we were to hit that maybe with a hammer or something, these rocks would move around a little bit. Okay, now compare that to our interstitial alloy, our jar of rocks where we've just filled it with sand. The sand is filling in the gaps now. So if I were to come along and hit this with a hammer, my rocks probably wouldn't move much, if any, at all, because there's no space in here anymore. The sand has come in and it's filled up all the space. So as a result, when you have an interstitial alloy and compare that to just a plain metal by itself, your resulting alloy is usually much more rigid. It's not nearly as malleable. Those atoms can't move because there's no empty space in there. So it's less ductile, it's less malleable, or in other words, it is harder than it originally was. And a great example of this is steel. Okay, steel, of course, is made of iron. Now let's imagine we're in the Iron Age and I've just discovered iron, so I made a nice sword of iron. Well, iron's pretty hard, so I start swinging at things, it's going to do some damage to it. Okay, but iron's a metal, metals are malleable, so my blade's going to get dull and it's going to bend a little bit. But if I take that iron and add some carbon to it, that's a smaller atom, it's going to go in and fill in the spaces. I am going to make an interstitial alloy, which we know as steel. And so now if I have a steel sword, now it's a lot more rigid and it's a lot harder. It doesn't bend as easily. It's not going to dull. The blade's going to stay sharper. So if I'm fighting you and you've got just a plain iron sword because you don't have mad chemistry skills like I do, I have my steel sword. I don't know if I'm going to win or not. I don't know how much my sword fighting skills are, but my blade is going to last a lot better than yours is. So we have an interstitial alloy. Okay, now of course the other type is where we have things that are very similar in size. You can see these guys here are pretty similar in terms of their size. So instead of filling in the gaps here, basically it's just replace. I mean, there could just as easily be a blue guy right here where this yellow guy is. They're very similar in size. So notice we still have a lot of spaces here. So this is called a substitutional alloy because they're almost interchangeable because of the same size. We can substitute the yellow for the blue. And because of this, the properties don't change a whole lot. These usually tend to still be malleable. There's spaces in here. So if we come and hit this thing with a hammer, these guys can move a little bit. Okay, so they're typically still fairly malleable, fairly ductile. The properties tend to often be an average of the two kinds of atoms that you have. The density is usually an average of the things that are together. For example, in the brass, the density would be about an average of the density of the copper and the atoms that put it together. Okay, so the properties still fairly similar to the two things when we have a substitutional. So now I want you to take a minute. On your paper, you have this question about our sulfur. So take a minute and write this answer down and answer this question, and we'll see what you said. Okay, well, hopefully when you talked about sulfur, you said no, sulfur is not held together by a loosely flowing sea of electrons. Now, part of your answer would be that sulfur is a nonmetal. Now, as a nonmetal, it has a higher ionization energy, a stronger attraction for its valence electrons. Remember, on the periodic table, okay, we have, as we go this way, the ionization energy increases. Okay, the effective nuclear charge gets stronger. So when we have our sulfurs and nonmetals that are over here, we have higher ionization energy. So it's got a stronger attraction for its valence electrons. And because it has a stronger attraction for its valence electrons, they are not loosely held. They stay pretty much with that sulfur atom. They're not just flowing from one atom to the other. Okay, so that's why nonmetals do not have these kinds of bonds holding them together. Okay, you have this question next. So take a minute, read it, write down an answer on your sheet, and we'll see how you do. Okay, so we're trying to figure out how the properties would compare of my nickel alloy to the original nickel. Okay, well, original nickel, we have a bunch of nickel atoms in here with spaces in between them. And we're going to come and put boron, make an alloy with boron. Well, boron is small. Okay, nickel has 4 energy levels of electrons. It's a much bigger atom than boron, who is only on the 2nd energy level. So when we make an alloy with nickel and boron, the boron is a lot smaller, so it's going to come in here and it's going to fill in the gaps. And so because of that, when we make an alloy with nickel and boron, we are going to have an interstitial alloy. And hopefully you wrote that down in your answer as part of your answer, that they make an interstitial alloy. And because it is an interstitial alloy, that means it is going to be a lot less malleable than just nickel by itself. So if you said something about our new alloy being less malleable or being harder or more rigid because those spaces are filled in, then you did a pretty good job. Okay, it probably will still conduct electricity. It's still going to be solid at room temperature, but it's going to be harder and more rigid. Okay, so we've looked at 2 types of forces holding particles together: ionic compounds, which are held together because we have opposite charges. That's a very strong force. There are no weak points in that ionic structure. And then we've looked at metallic substances now, held together by that loose sharing of delocalized electrons, that sea of electrons, which is also a strong force holding those together, making most of them solids at room temperature. So in later videos, we'll look at some of the other types of forces. Hope you enjoyed.